Hello everyone, welcome to this video. In this video we'll be discussing about example of permutation group. So let's see the example of symmetric group S3. Now this group S3, this denotes the set of all one-to-one functions which are defined from the set 1, 2, 3 to the same set, right? So here under this set we have the operation of function composition, as I have told you previously when defining the permutation group. So S3 under the operation of function composition, it forms a permutation group and this has exactly 6 elements. So which all 6 elements are a member of the group S3? Let's see them quickly. So here the 6 elements, they are defined like this. For the permutation 1, for the numbers 1, 2, 3, the one permutation is we do not change anything to it. So 1 would go to 1 only, 2 would go to 2 only, and 3 would go to 3 only. So this E doesn't change anything, right? Epsilon. Then we have alpha, where 1 goes to 2, 2 goes to 3, and 3 goes to 1, right? So we have the sample cycle that 1 goes to 2, then 2 goes to 3, and then 3 goes to 1. So this is a permutation. And in alpha square we define 1 goes to 3, 3 goes to 2, and 2 goes to 1. So here we say 1 goes to 3, 3 goes to 2, and 2 again comes to 1, right? So here we have this permutation alpha square. What is beta? Beta is keeping 1 as fixed. So it is keeping 1 to 1 only, and it is taking this 2 to 3 and 3 to 2, right? So 2 to 3 and 3 to 2. In alpha beta, what is happening? 3 is kept fixed. So 3 is moving on to itself, and 1 is moving on to 2, and 2 is moving on to 1. So you see we have 1 goes to 2 and 2 goes to 1 here in this case. And in case of alpha square beta, we have 2 kept fixed, right? And 1 would go to 3 and 3 would go to 1. 1 goes to 3 and 3 goes to 1, right? So these are the 6 elements here within the group S3. Now for this group S3, is it really a group? So for that we have to check the group axioms for this. So first of all, for associativity, obviously function composition, that is a binary operation, so we do not have to check the closure property. For the associative property, we know function composition, that is associative in nature. So therefore this group here is also contains the property of associativity. Next, let us see the identity. Here it is clearly visible that the permutation which is given by this epsilon act as your identity, because it keeps every other element as fixed. So it will move 1 to 1, 2 to 2, 2, 3 to 3. And moreover, if you multiply this with any member here, so let me show you how this works. So this is your identity, and what is alpha? Alpha is your 1, 2, 3 goes to 2, 3, 1, right? So when you solve this thing, you would have 1, 2, 3. Now here we will be moving from right to left. So 1 goes to 2 and 2 goes to 2, right? So 1 goes to 2 and 2 goes to 2. We have 2 here. Then 2 goes to 3 and 3 goes to 3. So we have 3 here. And 3 goes to 1 and 1 goes to 1. So that means we have 1 here. So you see this thing is what? This is your alpha, right? This is same as this thing. So basically when you apply this epsilon onto this alpha, you are getting back alpha. So this epsilon act as identity of the group. So second point is done. The identity exists and it is present within the group. Now next, for the third point, let's see the inverses. So we have to check the inverses for each and every element. So I have written that alpha is the inverse of alpha square. How this is so? You may check this thing, that alpha is the inverse of alpha inverse. So that means when you compose alpha with alpha square, you should get identity. Let's see, do we obtain identity? So when you compose alpha with alpha square, so you have to multiply them both, so that we would have the composition 1, 2, 3. So for 1 we have 3 here, for 3 we have 1 here. So 1 goes to 1, right? So under 1 we have 1. Next, let us see the next thing. For 2 we have 1 here, and for 1 we have 2 here. So under 2 we should write 2 here, right? So for the next element, 3, under 3 we have 2 here, under 2 we have 3 here. So under 3 we should write 3, right? So under 3 we should write 3, and notice that this is what? This is your epsilon permutation. So therefore alpha into alpha square is the epsilon, which is the identity of the given group. So therefore alpha and alpha inverse, alpha and alpha square, they are inverse to each other. For the next elements, we see that alpha square beta is the inverse of itself. Again, alpha beta is inverse of itself, and beta is the inverse of itself. So to verify this thing, let's see for alpha square beta. If you compose alpha square beta with alpha square beta only, you would have the permutation, which is the epsilon. How this is? So for under 1, we'll be moving from right to left. Under 1 we have 3, under 3 we have 1, so 1 goes to 1, 1 goes to 1, right? Next, for the element 2 here, we have 2 under 2, and here under 2 we have 2. So 2 moves to 2. So 2 moves to 2, right? For the element 3, we have under 3 the element 1, and under 1 the element 3. So 3 goes to this 3. So 3 goes to this 3. So what is this permutation here? This permutation is the epsilon permutation. So therefore both of them, they are inverses to each other. So alpha square beta is the inverse of itself. Similarly, beta is the inverse of itself, and similarly alpha beta is the inverse of itself. You can verify all these things. So therefore the inverse of each of the element exists in the given set. So therefore third property is also satisfied. Now moving forward and checking the commutativity here, we can take the element beta alpha and compose it. So we can take this beta and we can take this alpha, right? We have to compose it. So what would be beta alpha? Writing down beta here first of all, and then writing down alpha. We have 1 2 3 2 3 1. We have to compose both of them. So again 1 goes to 2, 2 goes to 3. So 1 goes to 3, 2 goes to 3, 3 goes to 2. So 2 goes to 2, 3 goes to 1, and 1 goes to 1. So 3 goes to 1. And what is this thing? This is not equal to alpha beta, right? Because here we have 3 to 1, and here we have 2 1 3. So as both of them, they are not equal to each other, so therefore the property of commutativity doesn't hold here. So therefore this S3 forms a non-abelian group. So I hope you understood this example. We'll be discussing about more examples in the next videos.